Hello, and welcome to a very special virtual version of Analytical Physics 3. This is a class that I am giving to make up for the class I missed last week for various kidney stone related hospital visits. So here we go. Today's topic is the photoelectric effect. So you might remember when we left off on Monday, we were talking about the Planck curve, how the frequency and wavelength of light is distributed in a blackbody spectrum. And Max Planck, in order to do that, had to assume that there was some minimum energy associated with oscillators in the walls of a certain cavity, of any cavity. He did not, in fact, make the leap to call light quantized itself. In fact, he was so disturbed by this, he didn't make much of a leap at all. It took Einstein, in fact, to do that as one of his 1905 papers, but we'll get to that in a second. So first of all, we need to know, though, what the heck the photoelectric effect is and why its explanation was so pivotal to paving the way for quantum mechanics. So this is covered in Thornton and Rex section 3.6, if you'd like to read along. And the basics of the photoelectric effect is this. You've got some metallic surface here, some metallic substance. And when you shine light on a metallic substance, electrons can come flying off of that substance. This is the photoelectric effect in a nutshell. So how does it work? Well, the idea is that if you look at the structure of a metallic surface, there are electrons which are free to move around the substance itself. This is what makes it a metal, right? These electrons, these are the electrons that move when current is carried through it, and so they have some mobility to move from atom to atom along within the solid itself. This is not a physical diagram within the substance, but sort of an energy diagram within the substance. And you can see that there's drawn a couple of electrons here, and electrons buried at various depths in the surface of the metal itself. So obviously, there are some electrons that are fairly near the surface, energetically and also physically, and other electrons that are buried deeper in the surface within the metal itself. And the idea is when a wave of light comes along, it can strike one of these electrons, it can impart energy to these electrons, and if it gives it enough energy, it can reach this 0 point. This is sort of the zero energy state of the metal. Once it can reach enough energy to have more energy than this level, the electron is actually liberated and can leave the metal entirely and be ejected, so to speak. So you can see it takes more energy, for instance, to liberate this electron than it does to liberate this electron. That's the basics of how this works. These electric waves of light that come in give some energy to these. You can consider these, if you like an energy diagram, balls at the bottom of this hill. If they give them enough energy, they can move up and be liberated from this well altogether. We're mostly going to be interested in these particular electrons that are the least energetically sealed within the metal itself. These are the easiest electrons to liberate, and so they become the most important ones when we're thinking about these photoelectrons that come flying out. Okay, so how does this work? Well, you can consider a device. Let's say we hook this up and we're shining our light on this substance and these electrons are coming flying out. We could hook this up in some substance such that, for instance, when we shine a light on this, those electrons can reach another metallic surface. And when they reach the other metallic surface, they can, if they're connected in a circuit, you can actually get some current that flows through the circuit simply by shining some light on the surface. Let's see a little bit how this works. I'm going to shine some light on it. You'll see some photoelectrons flying out at various levels, at various speeds, but they're all making it across, and therefore we have some very small current just by shining a light on the side that's developed in the circuit itself. And so this is sort of a photoelectric device that we can use to make some experiments and see how the photoelectric effect itself works. Now, interestingly, the more energetic the more intense you make the light. So we've got a monochromatic light, meaning it's got a single wavelength, in this case of 406 nanometers. This is right at the blue end of the visible part of the spectrum. So these are very blue, indigo, violet, whatever you want to call this color, light waves that are hitting this particular surface. Let's see though how the current that we get depends on the intensity of this light that we're shining on. So I'm just going to turn it up. I'm not going to change the frequency or the wavelength of this light. I'm just going to make it more intense. I'm going to turn up the light bulb. Now let's see what happens. You turn it up, you can see the current going up here. You can see it on the plot here, the current's going to go up. And this makes sense. All of this makes sense classically, actually, right? If you have a more intense light, what does that mean classically? It means that the amplitude of the electromagnetic wave is higher. It means you're imparting more energy to the electrons. It means that they can, more of them are liberated and you get a higher current. So this is not surprising at all. In fact, this is exactly what you expect classically from these photoelectric devices. So far classical, so what else can happen? We can apply a voltage between these two, right? So right now there's no voltage, so these guys are just flying along with no magnetic force at all. But if we apply a voltage in the opposite direction, in other words, let's make a 0.4 volt, so I'm giving it some negative voltage, which means I'm putting some negative charge on this side and some positive charge on this side. Since these are negatively charged electrons, they're feeling a repulsive force from this side and they're feeling an attractive force to this side. So this makes it more difficult for these electrons to bridge the gap between these two surfaces, right? So we expect that the current is going to go down as we increase this voltage. And in fact, let's see what happens as we increase the voltage, meaning make it more negative. The voltage, the current, it goes quickly to zero, actually. And in fact, if I go in the opposite direction, it doesn't change it much at all, other than making those guys go over there with a bit more energy. So interesting, this is, again, still completely understandable from classical physics. We have some negative voltage, and eventually this thing will just drop straight to zero. So eventually he'll stop all of them, okay? That makes sense. Okay, so where do we run into problems? What is the problem? So here's the problem. There is a point, and let's turn this down to zero. Actually, let's turn this like 50%. Let's say 20, 30%. Okay. I'm going to move this to a negative 1 volt, right? This is a much more, so at this point, there's enough voltage here that none of the electrons that are liberated from this particular photoelectric device can bridge the gap. Our current is zero. Okay, so now here is where classically we would say, if we increase the intensity of this beam, the intensity of this light wave becomes more intense. If we go back to our graph here, it should be that the energy being delivered by this particular wave is higher, and it should be that we can start to liberate some of these electrons that are just barely hanging on here at the least confined region. And yet, here is the thing that happens. You increase the intensity from 30 to 40 to 50 to 60 to 70 to 80 to 90. It doesn't matter how intense you make this light. You can double it, you can triple it. There is a certain voltage above which no electrons will ever cross this boundary. Your current will always be zero. And that is not explainable classically at all. Apparently, there is some maximum energy for this particular wavelength of light that no matter how intense you make it, you cannot give, there's some maximum amount of energy that it can be given to these electrons. And it happens to be that it's enough that it can't. So let's think about this, right? The more intense you get, electrons are still being liberated. That's not the problem. But they're not being liberated with enough energy. We basically have, see if I can do this in real time. We basically have another hill here to climb, right? This is however much we want to make that voltage, we can make this hill as high as we want to make it, right? So in order to both get out of the metal and also overcome that voltage difference, these electrons have to be given enough energy such that their kinetic energy is enough to overcome this potential energy of the voltage difference. And there's a point at which these electrons no longer have enough energy, no matter how intense we make this light. That's the weird thing about the photoelectric effect. Now, if we make this voltage a little bit smaller, like 0.4 volts, well, now, actually, we have a small enough barrier now that some of them do make it. And now we do have the case where increasing the intensity does increase the current, but below this particular stopping voltage, whatever it happens to be, it's not 0.6, is it 0.8? 0.8. At 0.8, it doesn't matter what the intensity of the light is, we get zero current flowing through. And so you can sort of see how this is going to work. We've got, if you make this 0.8 and you get this thing, that is exactly how much energy is being imparted to these least bound electrons, such that they can just barely make it across, or barely just can't make it across. At 0.6, they still can. With this barrier being 0.8, they can't both get out of the metal, liberate themselves from the metal, and also overcome this potential difference. So there is some maximum energy the electrons can get, no matter how intense the light is. Okay, what if we change the frequency or the wavelength of the light? How does that affect the stopping voltage? Let's take a look. So this is a blue photon. Let's try, let's say, a green photon or a red photon even. 600. Let's try, like, I don't know, 550 or so. There's about 550. Okay, now let's bring the intensity down. Let's bring the voltage to 0, and let's chart this over again. Okay, we're going to shine some light on it. Uh-oh, this is very weird. Let me try an intermediate one, maybe 480. Okay, here we've got we've got some current here. This is slightly redder, although it's not still red. It's still kind of blue, but it's going to take less voltage to stop this thing. And in fact, when I get to even 0.2 volts at this point, so as I increase the wavelength, in other words, decrease the decrease the frequency, the stopping voltage has gone down. Instead of taking negative 0.8 volts, it only takes 0.2 volts to stop all of them from leaving the metal out, from bridging this gap. And if I go too long a wavelength, even 550, it does not matter how intense I make this light. It doesn't matter if I have 0 volts or positive volts or how many volts I have. Let's get those residual electrons out of there. It does not matter how intense I make those lights or what I make this voltage. 0 photoelectrons are created ever if this wavelength is too long or the frequency is too low. And that's not explainable at all classically. So what the heck is going on? Here is a let's just look at. So this is again the view from the book about what's happening. Again, this is the photoelectric device. Incident light comes in, electrons are liberated, closes the circuit. You get some current going through. You can apply some voltage between these, and this is the sort of the graphs we were plotting, right? For 0 applied voltage, if you increase the intensity of the light coming out, you increase the current that you get through that surface. And this is, again, expected classically. If you apply a negative voltage, you expect this to go down. But classically, you would not expect all of these to go to 0 at exactly the same point. You would expect this more energetic light, more intense light, to take up a higher voltage to get to 0. The fact that they all go to 0 at the same point is weird and not at all explainable classically. Okay, so what is the explanation? Enter Einstein. Einstein, if you don't know, I'm sure you know who Einstein is, but he wrote 3 or 4 papers in a single calendar year, 1905, that completely either created or changed entire branches of physics. It's one of the most amazing single year outputs of any scientist at any time ever. It is astonishing. And so what did Einstein say? Einstein realized that he could explain this if light comes in packets. And I'm not sure if he coined this word, but they became to be known as photons, particles of light. And these particular light particles, whose energy is E equals Planck's constant times the frequency of that light. So this is weird, right? The debate over whether light is a particle or a wave has been going on since the Newton's time. And, we have been talking all semester about how light is a wave and how it diffracts and how we can characterize its wave and how it has a oscillating electric and magnetic field. All of that is still true. And yet, it is also a particle. You're going to learn a lot more about this wave-particle duality next semester. It's a very weird thing. There's all sorts of weird consequences and uncomfortable things that happen with this, but you'll explore that in great detail next semester. For now, you can think of these packets, again, there's a wave, but it's a sort of a beginning and end point to a wave that has a fairly short time or space dimension to it. And so you can think of these individual photons as wave packets. They have a wavelength, but they also have a discrete amount of energy and a discrete amount of spatial size. So let's go back to this channel argument, right? And think about these photons, these electrons right here. A single electron, the kinetic energy or the energy at all imparted to one of these electrons has to come from a single photon, right? So let's think about that. The kinetic energy of an electron leaving the solid must be due to a single absorbed photon. And so we can talk about the total kinetic energy of that electron. It must be the energy of the photon itself minus this energy. And I'm going to call this energy specifically the energy of the least bound electrons within the metal. I'm going to call that Greek letter phi. And this is known as the work function of the metal. And this is it's a function in that if you're talking about zinc, or you're talking about steel, or you're talking about brass, or you're talking about tin, the work function will be different for each of these metals. And all the work function is, but it's a constant for those particular metals. So for instance, sodium has a particular work function, and it's just a number, and it's an energy, so many electron volts, say. And so that tells you how much energy is required to take it from this least bound state to being free, right? So the total kinetic energy of the electron after it leaves the solid is the total energy that was absorbed minus the energy that it took to get it out of the metal itself. And that, in fact, is the work function, or phi, right? So this is just conservation of energy. This is the total energy that you've given to that particle. This is how much energy it took to liberate it from the metal, and this is how much is left to have kinetic energy of that electron after it leaves the metal. So we can say a little bit more. We know that the kinetic energy of an electron is 1/2 times the mass of an electron times the maximum squared. It's not really what we want. Let's see if we can do this. Vmax squared And that has to be equal to the energy of the photon, but we know the energy of the photon. That's just Planck's constant times the frequency of that photon minus the work function. And we call this actually work function. I'll spell it out in words here, and we'll put the symbols down here. This is the photoelectric equation. This is just conservation of energy for these absorbed photons, but it has built into it this discrete packet of energy associated with these particular wavelengths. And so this kinetic energy, as long as the extra barrier that you give it is less than the kinetic energy, then you'll still have some photoelectrons making it across the bridge, and you'll still have some current. If you make your barrier too high, then even the most energetic of your particles won't have enough energy to actually bridge the gap, and your current will go to zero. Okay, that's basically the photoelectric effect. You'll do, or I'm not actually sure what you're going to do this semester. In normal semester, you would have done an experiment where you shine light of various wavelengths onto a device, and you measure the stopping voltage, how much voltage it actually takes to make this current go to zero. By doing that, you actually can measure and get a value for Planck's constant itself. But I'm not sure how that's actually going to work this semester. You'll have to let me know how that goes. Okay. So I think that's all you really need to know for the photoelectric effect. You can certainly read more about it in Thornton and Rex. We'll come back and start again on Monday. And on Monday, we will be, in fact, starting our discussion of one of the most exciting topics that we cover all semester, and that is special relativity. Another one of Einstein's papers in 1905. So I hope you are enjoying your break and have had a restful time. And I will look forward to seeing all of you on Monday afternoon.